All right, let's break down the concept of air pressure and winds in the simplest way possible. Think of me as your guide, explaining these invisible forces that shape our weather. What is air pressure? 1. Air has weight. Just like everything else, air is made up of tiny particles called molecules. These molecules have weight. Because of gravity, the air around us is pulled down toward the earth. This creates pressure. Think of it like this. If you stack books on top of your hand, you start to feel the weight. Air pressure is similar. It's the weight of all the air above us pushing down on everything. 2. Air pressure is a pushing force. Imagine a balloon. When you blow air into it, the air inside pushes against the balloon's walls. That's air pressure. In our atmosphere, air pressure pushes in all directions, up, down, and sideways. 3. Air pressure changes with altitude. The higher you go, like climbing a mountain, the less air is above you. This means there is less weight, and therefore less pressure. This is why mountain climbers sometimes use oxygen tanks. They are high up where the air is thinner, meaning less pressure and fewer oxygen molecules. How does air pressure affect weather? 1. High and low pressure areas. Imagine you are on a playground. If all the kids, air molecules, gather in one spot, high pressure, it gets crowded and pushes outward. Where there are fewer kids, low pressure, there's more space. In weather terms, high pressure areas are where air is piled up and pushes down more on the earth. Low pressure areas are where there is less air pushing down. 2. Movement of air. Air moves from high pressure areas to low pressure areas. This movement of air is what we call wind. So wind is just air moving from where there's more air, high pressure, to where there's less air, low pressure. 3. Transporting heat and moisture. Winds carry more than just air. They also move heat and moisture from one place to another. This is why a place can suddenly feel warmer or colder when the wind changes direction. Why are winds and air pressure important? 1. Temperature control. Winds can bring warm air from one region to another, affecting the local temperature. For example, a warm breeze from the ocean can make a coastal area feel warmer. 2. Precipitation, rain and snow. Winds can also carry moisture from oceans or lakes to land. When this moisture cools down, it can fall as rain or snow. This is how air pressure and wind patterns control precipitation. 3. Weather forecasting. Understanding air pressure and wind patterns helps meteorologists, weather scientists, predict the weather. For example, if they see a low-pressure area moving toward a city, they might predict rain or storms because low pressure is often associated with clouds and precipitation. Simple example to understand air pressure. Imagine you are holding a water-filled balloon. The water is like air molecules. If you squeeze the balloon, increasing pressure, the water pushes harder against the sides. If you let go, the pressure decreases and the water doesn't push as hard. This is similar to how air pressure works. More air molecules mean more pressure, and fewer molecules mean less pressure. Key points to remember. Air pressure is the weight of air pushing down on us. Winds are caused by differences in air pressure. Air moves from areas of high pressure to low pressure. These invisible forces help transport heat and moisture, affecting temperatures and causing rain or snow. High pressure areas usually mean clear, sunny weather, while low pressure areas can mean clouds and rain. By understanding these basic ideas, you can better understand how weather works and how meteorologists predict it. Let's break this down even more simply. The relationship between pressure, density, and temperature. 1. What is air pressure? Air pressure is the force that air exerts on everything. Imagine the air pushing down on you like the weight of a heavy blanket. At sea level, this blanket is thicker and heavier than it is high up in the sky. 2. How air pressure changes. Density. This is how many air molecules are in a certain space. If the space is small and the molecules are packed closely together, high density, the pressure is higher. If the space is larger with fewer molecules, low density, the pressure is lower. Temperature. When air gets warmer, its molecules move faster and spread out. This can make the pressure increase if the density stays the same. If the air is cooler, the molecules are slower and closer together, which can lower the pressure if the density is unchanged. The gas law. The gas law tells us how pressure changes with density and temperature. Pressure, prop text density, times text temperature. This means if you increase density or temperature, the pressure will also increase, assuming the other factor is constant. Pressure at sea level versus high altitudes. 1. Sea level pressure. At sea level, the air pressure is around 1,034 grams per square centimeter, or 14.7 pounds per square inch. This is because there is a lot of air above you pushing down. 2. Why you don't feel this pressure. Even though this pressure is pushing down on you, your body pushes out with the same force. This balance means you don't feel the weight of the air. 3. Pressure at high altitudes. As you go higher, like on a mountain, there's less air above you. This means the pressure is lower because fewer air molecules are pushing down. At the top of a very tall mountain like Mount Everest, the air pressure is only about 1/3 of what it is at sea level. With less pressure, the air has fewer oxygen molecules, which makes breathing harder and can cause issues like nosebleeds. Summary. Air pressure, the force of air pushing down on you. Density. More packed air, high density, means higher pressure. Less packed air, low density, means lower pressure. Temperature. Warmer air can increase pressure if density stays the same. Cooler air can lower pressure if density stays the same. High altitudes. Less air pressure at higher elevations makes it harder to breathe and can cause health issues. I hope this makes it clearer. All right, let's go through how we measure air pressure in a very simple way. How we measure air pressure. 1. Mercurial barometer. What is it? It's a tool used to measure air pressure accurately. How does it work? Imagine a long glass tube filled with mercury, a heavy liquid. The tube is closed at one end and open at the other. Experiment. In 1643, a scientist named Evangelista Torricelli did a famous experiment. He filled a long tube with mercury and then flipped it upside down into a dish of mercury. When he did this, the mercury inside the tube dropped, but it stayed at about 30 inches high. Why? The air pressure pushing down on the mercury in the dish is the same as the pressure of the mercury inside the tube. So, the height of the mercury in the tube tells us about the air pressure. 2. Standard pressure. What is it? At sea level, the standard air pressure is about 1,013.25 millibars, or 29.92 inches, or 760 millimeters of mercury. Units. A millibar is a unit of pressure, and it's related to a force called a dyne. A dyne is a tiny unit of force, similar to the weight of a very small paperclip. 3. Correcting measurements. Why? We need to adjust measurements to compare air pressure at different places. How? We make corrections for things like altitude, how high the place is above sea level; temperature, how hot or cold it is; latitude, how far north or south you are from the equator; instrument errors, any mistakes the measuring tool might make. Other types of pressure measuring tools. 1. Aneroid barometer. What is it? A type of barometer that doesn't use mercury. Instead, it uses a small sealed metal box that changes shape with air pressure. 2. Altimeter. What is it? A special barometer used to measure altitude, how high up you are. 3. Barograph. What is it? An automatic barometer that records air pressure changes over time on paper. 4. Microbarograph. What is it? An extremely sensitive barograph that can detect very tiny changes in air pressure, like small waves or big events like a nuclear explosion. Summary. Mercurial barometer. Uses mercury in a tube to measure air pressure. Standard pressure. At sea level, it's about 1,013.25 millibars, or 29.92 inches of mercury. Corrections. Adjustments made to compare pressure readings from different places. Other instruments include aneroid barometers, altimeters, barographs, and very sensitive microbarographs. These tools help us understand and track changes in air pressure, which is important for weather forecasting and scientific studies. Let's break down the topic of variations in air pressure and how they affect the weather in the simplest way possible. Variations in air pressure. Air pressure changes. Air pressure is not the same everywhere. It changes from place to place and from time to time. Standard sea level pressure. On average, the air pressure at sea level is about 1013.25 millibars, EMB. This is the typical value we use as a reference. Range of sea level pressure. The air pressure can range from 982 lower to 1033 miles higher around the world. Extreme records. The highest air pressure ever recorded was 1075.2 mil in Irkutsk, Siberia in 1893. The lowest recorded was 877 blows in the Mariana Islands during a typhoon. 2. Why air pressure changes matter. Air pressure changes are very important in understanding and predicting the weather. High air pressure generally brings clear and stable weather. Think of sunny, calm days. Low air pressure often brings bad weather like rain, storms, or snow. Think of cloudy, windy, and rainy conditions. 3. Rising and falling air pressure. Rising air pressure. If the air pressure is going up, it usually means the weather is getting better. The skies are clearing, and the weather is becoming more settled. Falling air pressure. If the air pressure is going down, it usually means that bad weather is coming. It could mean more clouds, rain, or even storms. 4. Influence of nearby areas. The weather at any specific place is often influenced more by the air pressure in nearby regions rather than the air pressure at that exact spot. Example, if a neighboring area has very low pressure, it might bring bad weather even if the local pressure is relatively stable. In simple terms, air pressure changes all the time and is different from place to place. High pressure usually means good, clear weather. Low pressure usually means bad weather like rain or storms. Watching how the pressure changes, rising or falling, can help predict if the weather will get better or worse. Weather nearby also affects local weather. It's not just about the pressure right where you are. Understanding air pressure and its variations helps meteorologists, weather scientists, predict the weather and prepare us for what's coming, whether it's a sunny day or a stormy one. Sure, let's go step by step to understand the concept of the pressure gradient in the simplest terms. 1. What is air pressure? Air pressure is the weight of the air pushing down on everything. Think of it like the weight of a blanket lying on you. The air is not visible, but it still has weight and pushes on everything, including the ground and us. 2. What is a pressure gradient? The pressure gradient is a way to measure how much the air pressure changes from one place to another. Imagine you are looking at a map and there are lines called isobars on it. These lines connect places that have the same air pressure. 3. Understanding the concept with an example. Let's think about going for a walk in a park that has two types of hills. Steep hill. This is like a big sharp hill where you climb up quickly. Gentle slope. This is like a small slow hill where you climb gradually. Now, imagine that air pressure is like the height of these hills. A steep hill is like a place where air pressure changes a lot in a short distance. A gentle slope is like a place where air pressure changes a little over a longer distance. Number 4. How the pressure gradient works. Steep pressure gradient. When the pressure changes quickly over a small area, like a steep hill, we say there is a steep pressure gradient. This causes strong winds because the air moves quickly from high pressure areas to low pressure areas. On a map, this looks like isobars that are close together. Weak pressure gradient. When the pressure changes slowly over a larger area, like a gentle slope, we say there is a weak pressure gradient. This causes light winds because the air moves more slowly. On a map, this looks like isobars that are far apart. Number 5. Why do winds happen? Air moves from high to low pressure. Air always wants to move from where there is high pressure, like the top of a hill, to where there is low pressure, like the bottom of a hill. This movement of air is what we call wind. Stronger gradient, stronger winds. When the pressure changes quickly, steep gradient, the air moves faster, causing stronger winds. When the pressure changes slowly, weak gradient, the air moves slower, causing lighter winds. 6. Visualizing with a real-life example. Imagine you have a bowl filled with water, representing high-pressure air, and a bowl with less water, representing low-pressure air. If you tilt the two bowls towards each other, the water will flow quickly from the fuller bowl to the less full bowl. The steeper the tilt, the faster the water flows. This is similar to how air moves between different pressures. A steeper pressure gradient, steeper tilt, causes faster winds, faster water flow. Then number 7, importance of pressure gradient in weather. Weather prediction. Meteorologists use the pressure gradient to predict the strength and direction of the wind. A steep pressure gradient indicates strong winds and possible stormy weather. A weak pressure gradient indicates calm winds and fair weather. Conclusion. Pressure gradient. It's like the slope of a hill for air pressure. Steep gradient, like a steep hill, causes strong winds. Weak gradient, like a gentle slope, causes light winds. Wind always moves from high pressure to low pressure, and the speed of the wind depends on how steep the pressure gradient is. I hope this makes the concept of pressure gradients clearer. If you have any more questions or need further explanations, feel free to ask. All right, let's break down the concept of diurnal variations in air pressure in a simple step-by-step way, as if I'm teaching it to someone with no prior knowledge. 1. What is air pressure? Air pressure is like the weight of the air pushing down on us and everything around us. Imagine the air is a blanket covering the earth. Even though we can't see it, it still has weight and presses down. 2. What does diurnal mean? Diurnal means daily or over the course of a day. So when we talk about diurnal variations, we are discussing changes that happen within 24 hours. Hasher 3. What is diurnal variation in air pressure? Diurnal variation in air pressure refers to how the air pressure changes throughout a single day. Think of it like a seesaw. Sometimes the pressure goes up and sometimes it goes down, all within 24 hours. 4. Why does air pressure change during the day? There are two main reasons why air pressure changes during the day. A. Insulational heating and radiational cooling. Insulational heating means the Earth gets heated by the sun during the day. Radiational cooling means the Earth loses heat at night. When the sun heats the Earth, the air gets warm and expands. This causes the air pressure to drop. At night, the Earth cools down. The air gets cooler and contracts, causing the air pressure to rise. B. Expansion and contraction of air. When the air is warm, it expands, like blowing up a balloon, and the pressure gets lower. When the air is cool, it contracts, like letting air out of a balloon, and the pressure gets higher. 5. Semi-diurnal oscillation. Two ups and downs. Semi-diurnal variation means there are 2 times during the day when the air pressure is high, maxima, and 2 times when it is low, minima. This is a bit surprising because if the pressure only depended on temperature, we would expect only 1 high and 1 low pressure each day. When do these changes happen? At the equator, the air pressure typically peaks around 10 a.m. and 10 p.m. These are the high points. The lowest pressures are usually around 4 a.m. and 4 p.m. These are the low points. Number 6. Why does this happen? The semi-diurnal oscillation is like a wave in the air pressure. Think of it like a heartbeat or a rhythm that happens twice a day. This wave is stronger at the equator, the middle of the Earth, and gets weaker as you move toward the poles, the top and bottom of the Earth. 7. Diurnal pressure variation and location. Near the equator, the changes in pressure are more noticeable. In middle latitudes, places like Europe or the US, these changes are less noticeable because other weather patterns, like storms, can mask or hide the small daily changes. High latitude regions, close to the North and South poles, the changes are even smaller. 8. Diurnal variations over different places. Continents versus oceans. On land, during the day, the air pressure changes more because the land heats up and cools down quickly. Over the ocean, the changes are smaller because water heats up and cools down more slowly. Coastal areas. Near the coast, where land meets the ocean, the pressure changes are more noticeable because of the different heating rates of land and water. 9. Irregularities in diurnal variations. Sometimes the daily changes in pressure are not regular. This is because of Storms. Big storms like cyclones can disrupt the normal pattern. Other weather disturbances. Things like cold fronts, warm fronts, or thunderstorms can cause irregular changes in pressure. 10. Seasonal variations in air pressure. Just like there are daily diurnal changes in air pressure, there are also seasonal changes. These changes are caused by how much sunlight, or insolation, different parts of the Earth receive during different times of the year. Here are examples of seasonal variations. Tropical regions, close to the equator. These places have small seasonal pressure changes because they get nearly the same amount of sunlight all year round. Middle latitude regions, like parts of the US, Europe, and Asia. These places see more significant changes because they have hot summers and cold winters. Polar regions, near the North and South poles. These regions also have small pressure changes because they are mostly cold all year. Natural 11. Key takeaways. Diurnal variation. Daily changes in air pressure due to heating and cooling. Semi-diurnal oscillation. 2 highs and 2 lows in air pressure every day. Factors affecting pressure changes. Location. Equator, middle latitudes, poles. Nearby land or ocean. Weather patterns, like storms. Seasonal variation. Changes in air pressure over the year due to the tilt of the Earth and how much sunlight different areas receive. Conclusion. Understanding air pressure and its variations helps meteorologists predict weather patterns and prepare for storms. It's like reading the heartbeat of the atmosphere to know what's coming next. I hope this explanation makes it clear. If you have any more questions or want to dive deeper into any part, just let me know. Here is the simplified explanation of basic atmospheric pressure patterns. 1. What is atmospheric pressure? Atmospheric pressure is the force or weight of the air pressing down on the Earth's surface. Imagine the air around you as a big, invisible blanket that covers the Earth. This blanket has weight, and it pushes down on everything underneath it. 2. What are isobars? Isobars are lines drawn on a weather map that connect points of equal air pressure. Think of isobars like contour lines on a hiking map that show areas of the same height. But instead of showing height, isobars show air pressure. These lines help meteorologists, weather scientists, understand and predict the weather. 3. Understanding pressure systems. There are 2 main types of pressure systems that affect our weather. A. Low pressure systems, cyclones or depressions. A low pressure system is an area where the air pressure is lower than the surrounding areas. On a weather map, this looks like a series of circular or elliptical isobars with the lowest pressure at the center. It is often marked with an L. How does air move in a low-pressure system? Because the center has the lowest pressure, air from the surrounding areas, where the pressure is higher, moves towards the center. This movement of air causes winds. Winds blow towards the low-pressure center. Due to the rotation of the Earth, this air doesn't move straight, but spirals. Coriolis force and wind direction. The Coriolis force is a result of the Earth's rotation. It causes moving air to turn. In the northern hemisphere, this makes the wind spiral counterclockwise around the low-pressure center. In the southern hemisphere, the wind spirals clockwise around the low-pressure center. What weather do low-pressure systems bring? Low-pressure systems often bring cloudy skies, rain, and stormy weather because they cause air to rise, cool, and condense into clouds. B. High-pressure systems. A high-pressure system is an area where the air pressure is higher than in the surrounding areas. On a weather map, this looks like a series of isobars that form circular shapes with the highest pressure at the center, often marked with an H. How does air move in a high-pressure system? In high-pressure systems, air moves away from the center towards areas of lower pressure. This air movement is the opposite of a low-pressure system. In the northern hemisphere, winds blow clockwise around the high-pressure center. In the southern hemisphere, winds blow counterclockwise around the high-pressure center. What weather do high-pressure systems bring? High-pressure systems are associated with clear skies and calm weather because they cause air to sink, preventing cloud formation. 4. What is a trough of low pressure? A trough is an elongated area of low pressure, not circular, but stretched out like a V. On a weather map, the isobars look like a V shape. In the northern hemisphere, the wider part of the V often points northward. 5. How do pressure systems move? Semi-permanent high and low pressure cells don't change much. They stay in more or less the same place and can be seen on long-term weather maps, like monthly or seasonal maps. Smaller, short-lived pressure systems move around and change quickly. These are the systems we often see on daily weather maps. 6. How do these pressure systems affect weather? Cyclones, low-pressure systems, usually bring bad weather like rain, clouds, and storms. Anticyclones, high-pressure systems, usually bring good weather like clear skies and sunny days. 7. Conclusion. Understanding how high and low pressure systems work helps us predict the weather. By looking at the patterns of isobars on a weather map, we can determine where it might rain, where it will be sunny, and even where storms may occur. These systems are part of the Earth's natural way of moving air and energy around, helping to create the diverse weather we experience. All right, let's learn about high-pressure systems, also called anticyclones, in the simplest way possible. What is a high-pressure system or anticyclone? 1. High pressure. Imagine the air around us like a giant blanket. Sometimes, in some places, this blanket is heavier, more air is pressing down, and in other places, it is lighter. A high-pressure system is where this air blanket is heavier, meaning there's more air pressing down in one spot compared to the areas around it. 2. How does air move in a high-pressure system? In a high-pressure area, the air pressure is highest in the center and gets lower as you move outwards. Because the pressure is high in the center, air wants to move from this high-pressure center to the areas around it, where the pressure is lower. Imagine the air like marbles on a hill. They roll away from the top, where they are packed tightly together, high pressure, to spread out more at the bottom, low pressure. 3. Wind direction in high-pressure systems. As the air moves outwards from the high-pressure center, it doesn't move in a straight line. Due to the Earth's rotation, in the northern hemisphere, like in the United States or Europe, the air spirals clockwise. In the southern hemisphere, like in Australia or South Africa, the air spirals counterclockwise. This spiraling movement creates a gentle, outward flow of air. 4. What kind of weather do high-pressure systems bring? High-pressure systems usually bring calm, clear, and sunny weather. Because the air is sinking towards the ground, it prevents clouds from forming. No clouds mean no rain, so the skies are usually clear. 5. What is a ridge or a wedge? Sometimes, instead of being perfectly circular, the high-pressure system can be more stretched out, like an oval or a ridge. This stretched out high-pressure area is called a ridge or a wedge. Imagine a long hill rather than a round mountain. 6. How are anticyclones different from cyclones? Cyclones, low-pressure systems, have the opposite conditions, low pressure in the center with air spiraling inwards. They usually bring cloudy, rainy, or stormy weather. Anticyclones, high-pressure systems, have high pressure in the center with air spiraling outwards, leading to clear and calm weather. Think of cyclones as areas where the air rushes in, like water going down a drain, and anticyclones as areas where the air spreads out, like ripples on a pond. 7. How big are high-pressure systems? High-pressure systems, or anticyclones, are usually larger than low-pressure systems or cyclones. However, they are generally less intense in terms of strong winds. The weather changes they bring are usually more gentle and stable. Examples in real life. Sunny days. When you have a week of sunny, clear skies with little wind, you are likely experiencing the effect of a high-pressure system. Calm ocean. In areas over the ocean, high-pressure systems can create calm seas with no storms or big waves. High-pressure systems are like big, heavy blankets of air pressing down on the Earth. They cause air to move outwards, creating calm and clear weather. The direction of air movement is clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. High-pressure systems are generally larger and bring more stable, less intense weather compared to low-pressure systems. By understanding these basic patterns, we can better predict and prepare for different weather conditions. Does this help you understand high-pressure systems better? Sure, let's break it down step by step. Understanding pressure and air movement. 1. Earth's rotation and air movement. Earth spins. The Earth spins around its axis like a top. This spinning affects how air moves. Coriolis effect. Because the Earth spins, air moving in different directions is deflected or turned. In the northern hemisphere, air is turned to the right, and in the southern hemisphere, it's turned to the left. This is called the Coriolis effect. How air moves. Warm air rises. At the equator, the sun heats the Earth's surface more than at other places. This makes the air above it warm and light, so it rises. Moving towards poles. As this warm air rises, it moves towards the poles, north and south, at high altitudes. 3. Cooling and sinking. Cooling down. As the warm air rises and moves away from the equator, it starts to cool down, becoming heavier. Cool air is denser, heavier than warm air. So as the air cools, it becomes heavier and starts to sink back down. 4. High pressure zones. Subtropical highs. The sinking air creates high pressure zones around 25 to 35 degrees latitude north and south of the equator. These areas are called subtropical high pressure cells. 5. Why it's dry. Drier air. As the air sinks, it warms up again. Warmer air can hold more moisture than cooler air, so the air becomes drier as it descends. Adiabatic heating. As the air sinks, it warms up without adding any extra moisture. This process is called adiabatic heating. Because the air is dry and warm, it doesn't have much moisture to make clouds or rain. Deserts. This dry, warm air leads to clear skies and very little rain. That's why many of the world's deserts are found in these high-pressure zones. Summary. 1. Warm air rises at the equator. Air near the equator gets warm, rises up, and moves towards the poles. 2. Air cools and sinks. As this air moves away from the equator, it cools down, becomes denser, and sinks. 3. High-pressure areas. The sinking air creates high-pressure zones around 25 to 35 degrees latitude. 4. Dry weather. The descending air is dry and warms up, leading to dry and clear conditions. This is why deserts are found in these high-pressure areas. This explains how the Earth's rotation and the movement of air create high-pressure zones and influence weather patterns, particularly leading to dry conditions in subtropical regions. Let's break this down into simple steps to understand how air pressure belts work around the Earth. Understanding pressure belts. 1. The basics of pressure belts. Pressure belts. The Earth has different areas where air pressure is higher or lower. These areas form belts around the planet. 2. Key pressure belts. 1. Equatorial low pressure belt. Location. Around the equator, 0 degrees latitude. Description. This is where warm air rises, creating low pressure. It's also known as the doldrums because it often has calm winds. 2. Subtropical high pressure belts. Location. About 25 to 35 degrees north and south of the equator. Description. Here, the air that has risen at the equator cools down and sinks. This creates high pressure. You find deserts here because it's dry. 3. Subpolar low pressure belts. Location. Around 50 to 65 degrees north and south of the equator. Description. This is where the cold polar air meets the warmer westerlies. Winds from the west. This clash creates low pressure. The area is known for stormy weather and clouds. 4. Polar high pressure belts. Location. Near the poles, 90 degrees latitude. Description. Extremely cold air sinks and creates high pressure here. It's very cold and dry. 3. How they form. Warm air rises. At the equator, the sun heats the Earth, causing warm air to rise and create low pressure. Cool air sinks. As the warm air moves away from the equator and cools, it sinks around 25 to 35 degrees latitude, creating high pressure. Meeting of air masses. Around 50 to 65 degrees latitude, cold polar air meets warmer westerlies. This clash creates a low pressure zone. Cold air sinks at the poles. Near the poles, the air is so cold that it sinks, creating high pressure. Real-life complications. Uneven Earth. The Earth's continents and oceans are not evenly spread out. This uneven distribution affects these pressure belts, making the actual pattern more complex than the simple model. Summary. 1. Equatorial low pressure. Warm air rises and creates low pressure. 2. Subtropical high pressure. Warm air cools and sinks, creating high pressure. 3. Subpolar low pressure. Cold and warm air meet, creating low pressure. 4. Polar high pressure. Cold air sinks and creates high pressure. Understanding these pressure belts helps us predict weather patterns and understand climate zones better. Let's break down the concept of the observed distribution of pressure on Earth, keeping it as simple and clear as possible. 1. What is pressure distribution on Earth? Pressure distribution. The Earth's surface doesn't have the same air pressure everywhere. Air pressure changes depending on where you are, and this forms patterns or belts around the planet. 2. What affects pressure patterns? Land versus water. The Earth's surface is made up of land and water. Land heats up and cools down faster than water. This difference affects air pressure. Northern Hemisphere, more land. There are more land areas in the Northern Hemisphere. Because of this, the pressure belts here are not perfect circles, but are broken up into smaller areas of high and low pressure called cells. Southern Hemisphere, more water. The Southern Hemisphere has more water, especially as you move closer to the South Pole. Here, pressure belts are more continuous because the water doesn't break them up as land does. 3. Key pressure patterns. Equatorial low pressure. Location. Near the equator, 5 degrees newtons to 5 degrees. Description. This is a zone of low pressure because the equator gets a lot of heat from the sun, causing air to rise. This rising air lowers the pressure at the surface. Example. Imagine standing in a room with a heater at the center. The area around the heater, equator, will have rising warm air, creating a low-pressure zone. Subtropical high pressure. Location. Around 30 degrees nens and 30 degrees Celsius. Description. As air rises from the equator, it moves toward these latitudes and cools down, sinking back to the surface, creating high pressure. But unlike the low pressure at the equator, this high pressure is not caused by temperature, but by the way air moves. Example. Think of a balloon filled with air. If you push the air down, like the cooling air in subtropical regions, it creates pressure at the bottom. Subpolar low pressure. Location, around 50 to 65 degrees and S, near the Arctic and Antarctic circles. Description. This area has low pressure because of the clash between cold polar air and warmer air from the subtropics. In the Northern Hemisphere, this creates separate low-pressure cells over oceans. In the Southern Hemisphere, it's more of a continuous low-pressure belt. Example. Picture two people pushing against each other. Where they meet, like cold and warm air, there's a lot of activity, but the overall pressure is low because the forces are spreading out. Polar high pressure. Location, near the poles, around 90 degrees and 90 degrees. Description. These areas have high pressure because the air is very cold and dense. The cold air sinks, increasing pressure at the surface. Example. Imagine a very cold, heavy blanket pressing down on a surface. That's what happens at the poles with the air. 4. How these belts actually look. Not perfect belts. The pressure belts are not perfectly circular or even. Because of land masses in the Northern Hemisphere, these belts are broken into different shapes and areas. In the Southern Hemisphere, because of more water, the belts are smoother and more continuous. 5. Additional notes. Dynamic causes. Some pressure areas, especially in the subtropics and subpolar regions, are not just because of temperature, but also due to how the Earth rotates and how air moves. Real-life example. The Sahara Desert is located in the subtropical high-pressure zone. This high-pressure belt means that there is sinking air, leading to clear skies and dry conditions, which is why deserts often form in these regions. Summary. Pressure belts. Zones around Earth where air pressure is either high or low. Land and water affect these belts, especially breaking them up in the Northern Hemisphere. Equator. Low pressure because warm air rises. Subtropics. High pressure due to sinking air. Subpolar regions, low pressure where cold and warm air meet. Poles, high pressure because of cold, sinking air. These concepts help explain why we have different weather patterns and climates around the world. All right, let's break it down in the simplest way possible, step by step. Nakshar 1. What is a pressure belt? Imagine the Earth as a ball with different zones or belts. Some places on Earth have low pressure, air is rising, and some have high pressure, air is sinking. There are 7 of these pressure belts. They alternate between high and low pressures. 2. Equatorial trough of low pressure. There is a special low pressure belt near the equator, the middle part of the Earth. This belt stretches from 5 degrees north to 5 degrees south of the equator. Ashnar 3. Why is there low pressure near the equator? The equator gets the most sunlight. This is called insolation. Because of the heat, the land and air near the equator get very hot. Hot air becomes light and starts to rise. This rising air causes low pressure because there's less air pushing down. Example, imagine blowing a balloon. As the balloon rises, the space below it feels lighter, like there's less air pressure. That's what's happening near the equator. 4. What happens when air rises? When hot air rises, it cools down and moisture, water, in the air turns into clouds. These clouds can cause heavy rain because of the moisture. The rising air in this belt has a lot of energy because of this moisture. Example, think about boiling water. The steam, water vapor rises up just like the hot, moist air in the equator. Ha5. Why is it called the doldrums? Near the equator, winds are weak and calm. Sometimes there's almost no wind at all. Because of this, sailors in olden times called this belt the doldrums, a place where ships could get stuck because there wasn't enough wind to move them. 6. Shifting of the belt with the sun. This low-pressure belt moves as the sun moves. In July, the sun is more towards the north, so the belt shifts north of the equator. In January, the sun moves to the south, and the belt shifts to the south of the equator. Example, imagine holding a flashlight above a globe. The area where the light shines brightest, the hottest part, will have the low-pressure belt, and it shifts as you move the flashlight. Nar 7. Why is it always hot and low pressure here? In this belt, it's hot all year because it's near the equator. Since it's always hot, the air keeps rising, so the pressure stays low all the time. Extra information, the air pressure is measured in millibars. In this region, the pressure is usually below 1013 millibars. Summary, the equatorial low pressure belt is a hot, calm, and moist region around the equator. It moves north and south with the sun's position throughout the year. It is a place where winds are weak, and ships could get stuck due to the calmness, which is why it's called the doldrums. Does that help clarify things for you? Let's break down the concept of the subtropical high-pressure belt in a simple way, step by step, for easy understanding. 1. What is the subtropical high-pressure belt? This is a zone of high atmospheric pressure located between the latitudes 25 degrees to 35 degrees north and south of the equator. It consists of multiple smaller areas called high-pressure cells. 2. How do these high-pressure cells form? These high-pressure cells are believed to be formed by the bright rotation of the Earth. Air in these regions is sinking from high up in the atmosphere, which increases the pressure on the surface below. Example, imagine pushing a balloon from above. The air inside the balloon moves down and the pressure on the surface increases. Hashraf 3. What happens to the air here? In these zones, the air is sinking, and when it sinks, it gets warmer and drier. This results in clear skies and dry weather for most of the year. Example, this is why many deserts, like the Sahara or the Arabian Desert, are found in this belt, because the sinking air prevents rainfall. 4. What are horse latitudes? The subtropical high-pressure zones are also known as horse latitudes. Historically, this name comes from sailors getting stuck in these calm areas with no wind to move their ships, and sometimes they had to throw horses overboard to lighten the load. Hash 5. Winds in this belt. In these high-pressure areas, the winds are light and variable. meaning they often change directions or are very weak. Sometimes, storms from outside this zone can cause strong winds, but that doesn't happen often. HAMAR 6, Seasons and Changes. The location and size of these high-pressure cells can change with the seasons. In the southern hemisphere, during winter, these high-pressure areas spread to nearby continents. In the northern hemisphere, during summer, these areas become bigger and the pressure increases. 7. Daily weather and high pressure. The size and position of these high-pressure belts can change daily due to various factors, so they are not fixed or permanent. The air in this region is stable because it is sinking, which prevents clouds and rain from forming. 8. Why are deserts located here? Since the air is sinking and dry, it doesn't allow much rain to fall. All the world's major deserts are located in this belt because of this constant dry weather. 9. How high do these belts go? These high-pressure zones can extend as high as 9,600 meters, 9.6 kilometers above sea level. 10. Structure of high-pressure cells. The structure of these high-pressure cells is not symmetrical, uneven. On the eastern side of the oceans, the air is more stable and dry. On the western side, the air is a bit more unstable and humid, which can sometimes cause storms. Summary: the subtropical high-pressure belt is found between 25 degrees to 35 degrees latitude, north and south of the equator. It consists of multiple high-pressure cells where air sinks, making the weather dry and calm. These zones are also known as horse latitudes, and they are home to many of the world's deserts because of the dry air. These cells change in size and location throughout the year due to seasonal changes. This explanation simplifies the idea of the subtropical high-pressure belt. Does it help you understand better? Let's break down the explanation of subtropical high-pressure cells in a very simple way. Imagine these high-pressure areas as zones on Earth where the air pushes down more heavily, creating a region of high pressure. What are subtropical high-pressure cells? They are areas located between 25 degrees and 35 degrees latitude, both north and south of the equator. These are important because they control the movement of air and influence the weather in these regions. These high-pressure cells are where the air sinks down after rising from the hotter areas near the equator. Now, let's explain how they form. 1. Dynamic factors. How air moves. Air rises near the equator where it's hot and then moves towards the poles, north and south. Around 20 degrees latitude, this air hits a barrier. It can't keep moving poleward, so it starts to sink back down towards Earth's surface. This sinking air creates high pressure because it piles up and presses down on the ground. Problem with this idea. This theory works, but sometimes the winds that push air north or south, called antitrades, are not strong or not present, so this theory doesn't always explain everything perfectly. Term 2. Polar air masses. Cold air from the poles. Another reason for the subtropical highs is the movement of cold air from the poles, north and south poles. Near the polar front, a boundary between cold and warm air, cold air masses can sometimes move towards the equator. These cold air masses bring high pressure with them, which can strengthen or regenerate the subtropical high pressure cells. Where does this happen? It mostly happens over the eastern parts of oceans, where cold air moves and meets cold ocean currents. This makes the pressure in these regions even higher. 3. Thermal factors. Effective temperature. The temperature difference between the hot tropics and the cold poles is another reason why subtropical highs form. Where there are cooler ocean currents, like in the eastern oceans, the air above these cold waters tends to sink, making the pressure higher. This is why subtropical highs are stronger in some areas, like over the eastern oceans, where the water is cooler. 4. Combination of both factors. Both the air movement, dynamic factors, and the temperature difference, thermal factors, work together to form these subtropical highs. Sometimes they help each other, making the pressure higher. Other times they cancel each other out, causing changes in the pressure cells. Summary in simple terms. Subtropical high-pressure cells are areas where the air sinks and creates high pressure. They are located between 25 degrees and 35 degrees latitude. Air movement from the equator and cold air from the poles both contribute to creating these pressure cells. They are stronger over the oceans because of the cooler temperatures there. These high-pressure cells change throughout the year because air movement and temperature differences are not always the same. Think of it like this. Imagine air is like water. At the equator, the water, air, heats up and rises. As it cools, it moves towards the poles, but it sinks back down around 25 to 35 degrees latitude, causing pressure to build up like water pouring into a container. This sinking air creates the subtropical high-pressure zones. Seasonal variations in pressure patterns. Let's understand how the pressure patterns change with the seasons in a very simple way. What are pressure patterns? Pressure patterns show where high and low pressure areas are on Earth. These patterns change with the seasons due to the sun's movement. How does the sun affect pressure patterns? 1. Sun's movement. The sun's direct rays move between two lines called the Tropics of Cancer and Capricorn. In July, the sun is directly overhead the Tropic of Cancer, northern tropic, so the pressure belts move northward. In January, the sun is directly overhead the Tropic of Capricorn, southern tropic, so the pressure belts move southward. Imagine, if you have a lamp shining directly on a ball, the hot spot moves as you move the lamp. Similarly, the sun's position changes, shifting the hot spots, pressure belts, on Earth. Seasonal variations in different regions. 1. Tropical regions. Near the equator, tropical regions, temperatures stay high all year. Pressure variations are small because the temperature doesn't change much. Example, think of a warm room where the temperature stays the same all the time. The pressure inside remains almost constant. 2. High latitudes. Far from the equator, high latitudes, there is a big difference in how the sun shines. Pressure variations are large because the sun's angle and the length of daylight change a lot. Example, in winter, the sun is low in the sky, making it colder. In summer, the sun is high and there's more daylight, making it warmer. This causes big changes in air pressure. Northern Hemisphere versus Southern Hemisphere. 1. Northern Hemisphere. There is more land and less ocean. Pressure patterns change more because land heats up and cools down faster than the ocean. Imagine, in summer, land gets really hot and creates low pressure. In winter, land gets really cold and creates high pressure. 2. Southern Hemisphere. There is more ocean and less land. Pressure patterns change less because oceans heat up and cool down more slowly. Example, think of a giant pot of soup. It takes a long time to heat up or cool down compared to a small cup of soup. The ocean, the big pot, it changes temperature slowly, affecting pressure patterns less. Distribution pattern in January. Let's break down the pressure patterns in January in the simplest way. How the sun affects pressure in January. 1. Sun's movement. In January, the sun is closer to the Tropic of Capricorn, which is south of the equator. This makes the equatorial trough of low pressure move south of the equator. Think of it. If the sun was like a lamp, it's shining more towards the south in January, making the hotspot, low pressure area, move south. Pressure patterns in different regions. 1. Southern Hemisphere, Australia, Africa, South America. Warm continents. The continents are warmer in January, they're summer, so they have low pressure because warm air rises. Low pressure cells. There are distinct areas of low pressure over these warm continents. Example, imagine a balloon filled with hot air. The balloon rises because warm air is lighter. Similarly, warm land causes air to rise, creating low pressure. 2. Northern Hemisphere, North America, Eurasia, cold continents. The continents are colder in January, they're winter, so they have high pressure because cold air sinks. High pressure cells. The high pressure areas are stronger over cold land, especially in places like Siberia. Example, when you put cold water in a balloon, it shrinks because cold air is heavier. This creates high pressure. Subtropical high pressure belts. 1. Northern Hemisphere. The subtropical high pressure belt is further north in January. The high pressure areas over the Pacific and Atlantic Oceans become weaker. Think of it. In January, the high pressure areas are like giant balloons that lose some air over the oceans. 2. Southern Hemisphere. The subtropical high pressure belt is between latitudes 30 degrees and 40 degrees S. It is well developed with high pressure centers over the oceans. Example. Imagine a big high pressure balloon over the southern oceans. This balloon is stronger and well developed in January. Subpolar low pressure belts. 1. Northern Hemisphere. The subpolar low pressure belt is broken up into separate low pressure cells over the oceans. There are two main low pressure areas, Icelandic low over the North Atlantic and Aleutian low over the North Pacific. Think of it. These are like isolated puddles of low pressure in the ocean. 2. Southern Hemisphere. The subpolar low pressure belt is well developed and continuous because there are no big land masses to break it up. Example. Think of a big continuous puddle around Antarctica that doesn't break up because there's no land in the way. Pressure changes in Antarctica and Eurasia. 1. Antarctica. Beyond latitude 65 degrees S, pressure gradually increases. Southeasterly winds from Antarctica confirm this high pressure. Example, think of the Antarctic area as having a big, steady increase in pressure as you move further south. 2. Eurasia. There is a large, deep high-pressure area in the east-central part of Eurasia. North America has a smaller high-pressure area because it's smaller than Eurasia. Think of it. Eurasia has a big, strong high-pressure area like a giant balloon. North America has a smaller, less developed balloon. Summary. In January, the sun's position causes pressure belts to shift. Southern Hemisphere, warm lands lead to low pressure. High pressure is strong over oceans. Northern Hemisphere, cold lands lead to high pressure. Low pressure cells are over the oceans. Subpolar low pressure, continuous in the south, broken up in the north. Antarctica and Eurasia. Antarctica shows a gradual increase in pressure, while Eurasia has a large high-pressure area. Visualize. Think of the Earth's pressure patterns like balloons and puddles changing with the seasons, influenced by the sun's land temperatures.